Hello, everyone. Here we have the second seminar about our collaboration between National Aviation University and University of Brasilia. And today I present another subject of our development, which is ramjet engines at the Chemical Propulsion Laboratory, talking about experimental studies and numerical simulation. If you have some questions, please let us know in the comments. So after my presentation, I will answer. I will try to make this talk about 40 minutes, so we will have about 20 minutes for discussion. There are lots of slides, so I will skip some of them. Maybe they will not be so interested for this first meeting, and then in future meetings we can cover more advanced topics. This presentation will be divided mostly in 3 parts. Part 1 will be about solid fuel ramjets. They are divided in molded grains and composite 3D printed grains. Our experimental activities on these type of engines. And then as an output, some publications which we made recently. And the second part is about liquid fuel ramjets, analytical and numerical studies, and test bench. And the third part I would like to spend on your questions and my answers. Okay, solid fuel ramjets. This is a topic which is extremely important, especially in Brazil and other countries when we are talking about missile application, when we are talking about engines with no moving parts, long range destination. There are many types of these engines, many designs, different design. For example, you can see a tactic missile from Brazil. It's, I think, an international joint project of development, AVT M300. And as a classical example, we can find TALs from the United States. The idea behind the ramjet is quite well known. It's simple. So this engine has is using air from external atmosphere as oxidizer and has a fuel charge on board. This fuel charge can be of different material. It can be self-sustained combustion, or let's say gas generator, or it can be just a solid fuel and it will burn together with air. We will talk about the second application, since we are working with hydrocarbon fuels and mostly paraffin and plastics. We will talk about this type of application. The advantage of ramjet is quite well known. It can work significantly longer than a conventional missile rocket engine. And so the distance of flight of this vehicle can be significantly longer. Significantly means many times longer. When the typical operation time of rocket engine is in terms of 1 minute or few minutes, this ramjet can work for many tens of minutes. So the distance would be, depending on size, can be huge. There are many of such developments all over the world we can find in publications. And here at the University of Brasilia, we work with a simple concept inside the university research projects. So we are working with the small-scale engine. All our engines are actually small-scale. The first part is about solid fuel ramjet engine working in different conditions. And we are studying how it can use hydrocarbon fuel, molded hydrocarbon fuel. We have specific goals as design and building of test bench. We have planning of test, development of control algorithm, modeling of inlet conditions and optimal supersonic diffuser, and test execution data processing. So here, talking about methods involved in this development, we can mention analytical and experimental empirical methods of ramjet design and analysis. And empirical methods, they are strictly related to experimental research. As you know, these are mathematical approximations of experimental data. So analytically, we can calculate diffuser. It can be an ideal diffuser or real diffuser for the engine, since flow must be decelerated and compressed from supersonic conditions to subsonic conditions inside combustion chamber. We can calculate thermodynamic cycle inside the engine analytically or by simple numerical method. We can calculate fuel regression or fuel burning inside combustion chamber. And we can calculate flow properties like flow modeling by some methods like area Mach number relation or method of characteristics inside the nozzle. When we are talking about more complex processes like compressible flow, viscous flows, combustion, fluid structure interaction, we need to involve numerical simulation. There is no other way, unfortunately, to calculate such process. And experimental research is also extremely important in ramjet development because we have to prove our concept. There is no way to simulate and calculate numerically the engine when it's not tested. So we have to build a test bench which is covering all the regimes for which the engines were designed. We have to plan test, we have to control flow and measure parameters and analyze errors. We have to estimate if we are working, if we are providing this experimental work in a correct way. On the right side of this slide, you can see the typical diagram of thermodynamic cycle of the ramjet engine. There are 3 cases here, and I will talk further about these 3 cases. The most important in this slide is that it shows different stages of flow passing inside. So it's a stage of compression inside diffuser, combustion chamber, part with increase of temperature and entropy, then expansion in the nozzle, and then exhaust to atmosphere, going back to the initial point of this cycle. There are many cases. Here I show just 3 cases corresponding to three different flight regimes, but in general, this diagram is quite flexible. It can adapt itself to any flight regime. And the most important is that the only one flight regime is a design regime, and other will be off design. Okay, talking about experimental setup that we have in our laboratory, you can see it here on this slide. It's so-called connected pipe test bench. Connected pipe means that we have a pipe coming from air tank, high volume air tank, passing through a series of valves and control units, measurement of mass flow rate, measurement of losses of pressure and the behavior of temperature inside, safety valve, and coming inside combustion chamber. So this high mass flow rate air is coming inside combustion chamber, and burning of fuel happens there inside the item 27 ramjet motor. Also inside combustion chamber, we measure pressure and temperature to ensure that inlet conditions on this engine will correspond to flight conditions of a real engine. We also have a safety system, nitrogen tank, which you can see here, number 30, which will extinguish flame when a test is finished. Another important part of this schematic is this igniter, which is also serving as a heat vitiator. It works on methane oxygen gas controlled by specific control valves. And this igniter is not just igniting the engine, but also keeping hot gas, simulating the diffuser compression and diffuser temperature rise. So this schematic allows us to change simulated altitude and simulated Mach number with varying quantity of air coming inside combustion chamber and the quantity of thermal energy coming inside the combustion chamber from igniter or gas vitiator. About plan of test, I will explain a bit later. We are simulating different cases. Actually, this engine, which I'm showing to you, it was tested hundreds of times as for now, and I think we studied quite well this engine. It's quite limited because we, for example, cannot simulate quite high values of Mach number and low altitudes because it requires extremely high thermal energy for gas vitiator. But we can cover, I think, the most used range of flight parameters as Mach from Mach 2 to Mach 4 and altitudes from 10 to 25 kilometers. Here you can see some pictures from our test bench and from control room. It's quite old pictures that I made maybe 5-6 years ago. And they show how the engine was mounted. It's a small-scale engine producing really a small amount of thrust. I think it's around 300 newtons just for test of concept. And on the left side, you can see the setup of this schematic, which I showed you on the previous slide. And on the right side, it's observation room with one monitor, which is showing the test, execution of test, and control computer. By use of LabVIEW, we can make a control of this execution of test, not just record parameters, but also control. And this, I think, these are just pictures, and then later I show you the videos, how it works. More closer looking to schematic of the motor, we can see here the part on the left, flow heater assembly. This flow heater is for simulation of diffuser inlet. On real diffuser, you can see the igniter, which is also a gas vitiator since it's quite powerful. We can use it as a gas vitiator. And there are air inlets on the sides, 4 pipes, four hoses of air inlet, methane inlet, oxygen inlet, and thermocouple and pressure sensor. Inside this volume of heater, we are creating conditions corresponding to conditions at the exit of the supersonic diffuser, and by thermocouple and pressure sensor, we are measuring these parameters. On the right side is the control valve, which I already showed you on my previous presentation. This control valve is serving to put a required amount of air inside this ramjet. So because since we are controlling the altitude and Mach number, we have to control also the amount of air coming into the system. So this control valve is working in real time and is adapting by PID algorithm and providing exactly the necessary values of mass inside the engine. It's worth also to say about the experimental test sequence that we are having on our test bench. This test sequence is divided into 4 parts. As you can see here, this red line is flow of methane inside the heat vitiator. The blue line is airflow. Okay, it's from very low value increases to its maximum or nominal value on time 2. Then the black line, I think it's temperature inside the heater. So the idea is that ignition of a ramjet motor, since it's working with the hydrocarbon fuel, in our case, it's paraffin or blend of paraffin with polyethylene, is quite difficult. So we have to have this test sequence from 0 to T1 and to T2 to ensure that our engine will ignite. In this case, we have a stage from 0 to T1 is ignition inside the igniter. It's characterized with extremely low value of air flow and methane. Then we ignite the fuel grain inside ramjet engine from T1 to T2. And during this period, we have extreme rise of temperature to ensure that this temperature will significantly exceed the self-ignition of fuel. So fuel temperature of ignition is somewhere is lower than the maximum of this temperature. And then from time 2 to time 3, we have a programmed operation of the ramjet engine. It's significantly higher, larger time that T1 or T2. But just for this schematic, I show it short, just to fit all in on one plot. Typical time of test which we provided from T2 to T3 was around 10 seconds, when from 0 to T1 or to T2 was around 3 seconds. We are testing this engine for a short time because of limitations of structure. Since we are not using for this engine any high resistant materials or thermally resistant materials or heat insulation or any means of thermal control, we are working inside the limits of material. When temperature of wall reach some critical temperature, this experiment is stopped. And then from T3 to T4, we close heat vitiator, we extinguish flame, and just with the inlet of cold air, this temperature reduces lower than flammability limit of this fuel, and process stops. From T3 to T4, maybe we need 5-10 seconds to cool down the structure to be able to approach to the motor. So this is the classical test sequence. I would like to remind you that these materials I'm showing you here, they are all published in the literature. So if you will be interested in some part of technical aspect or some part of this development, you can find or I can forward you the publications on these topics. Here we can see results of motor operation. We tested this motor in different regimes. I call these regimes on the left low heating power. It corresponds to Mach 3 and 12.8 kilometers of altitude. And high heating power, it corresponds to Mach 4 and 18.7 kilometers of altitude. And as you can see visually, the higher heating power and the higher Mach results in significantly lighter, brighter flames, and consumption of fuel, of course, increases, and thrust required increases. It's just because flying at higher Mach values, we have to have very much more significant thrust than for Mach 3. So changing from a little of Mach number, you know that kinetic energy is increasing in square. So we have to provide significantly higher thrust of this engine. And our test bench is allowing us to regulate this mass flow rate and heating value, so we can ensure that our system is operating well. Here are four pictures for each case. Picture 1 is about ignition of igniter. Picture 2 is about solid fuel ignition, where you can see that flow is still looks subsonic for solid fuel ignition because the air mass flow rate is low. And here, and for picture 3, main propulsion, we already can see diamond shock wave, so flow is supersonic inside the nozzle. And cold flow extinguishing the flame. For low heating power, flame extinguished naturally, I'd say automatically. And for high heating power, flow did not extinguish immediately. It reduced with time, and then with use of nitrogen, we could stop the process of combustion of fuel inside combustion chamber, because it has a significant, still significant heat inside combustion chamber. So the process doesn't stop immediately. This is the test. Here you can see ignition, main flow operation, main engine operation, nominal regime, and then flame extinguishing. I think this test was something close to 5 seconds, 5 seconds test. And this is how it worked. Really nice didactic experiment, and many of my students made their final works on this engine, published several papers. So it was a nice small experiment. You can see that it's a bit messy, the test bench by itself. And I think it's normal because since we are working with propellants, we are working with high humidity in Brazil. We are working with not very clean technology, with fuels and paraffin and plastics, etc. So this is a working condition. Nowadays, this test bench is completely different. It's not like you can see here, but at that time, it served quite well for our research. On the side, you can see a larger ramjet. I will talk about it a bit later. Okay, and this is for high power test. Okay, this is high power test, and as you can see, motor was working quite interesting operation. When we provide this together with our students, with our colleagues, it was a lot of fun to do this. This research motor is relatively small, so it allows us to change parameters fast, to adapt. Is not that expensive to operate. As a result, we can see here some data. They are parameters on the inlet of flow in terms of pressure. Different pressures we are simulating in point 10. Just to show you where is point 10, I think it was not really clear. Point 10 is this pressure after the control valve, before the non-return valve. So this pressure which we are controlling with valve number 9. Okay. And inside the combustion chamber, we have more or less same pressure independently on pressure level on the control valve, because the fuel is the same fuel grain. And it means that thermal energy provided to this combustion process is nearly the same. We are always working with excess of oxidizers, so amount of fuel is significantly smaller than amount of oxidizer, and fuel is defining the temperature. We can see here on the right the flow conditions for different cases. Here I show just 15 cases for different mass flow rates of air, mass flow rates of fuel, temperature inside combustion chamber, and pressure inside combustion chamber, and the exit Mach number. As you can see here, the variation, there are different variations. This exit Mach number is not Mach number of flight. This is just Mach number on the exit of the nozzle. Temperature inside combustion chamber was not measured. It was calculated. It was calculated by RPA, I think, or CA. I think, and here there is one error on experiment 10. It's not that small temperature. I think we have some small error on this table. So sorry about that. After making lots of experiments on this ramjet and combining it with the typical diagram for ramjet Mach 2 specific impulse, we can see that our experiments lie inside the classical ramjet range. So we can reach specific impulse around 1000 for low heating power. For high heating power, we can reach up to 1600 seconds specific impulse, and the flight regime will also strictly depend on the amount of heat which we are providing from gas vitiator, from Mach 2 2.2 to Mach 4 at most. So this engine definitely has limitations, but as we know, any ramjet engine has limitations because it has to operate only in supersonic conditions, so it must be accelerated at some moment. Conclusions about this section are stable operation on various regimes. The regression rates were measured, the specific impulse, as you can see here, for different cases, and two-stage ignition mechanism provided reliable ignition. As the result of this part of development, we have published two really nice papers. I will show you, and if you will be interested, you can find them also. They are available. online. There is a paraffin-based ramjet missile preliminary design, and it was published in Advances in Aircraft and Spacecraft Science last year. And this year, I think in November 2024, was published a chapter of a book about application development of supersonic ramjet anti-ship missile using space standards and rocket technology. This is an extension of previous works in application of our research to some real structure. So we have published the background for preliminary missile design, considering this technology of solid fuel ramjets. And I think we can quite fast provide any kind of preliminary estimation of such type of device. If you will be interested in some specific aspect, I can answer your questions a bit later. A second part of my presentation, first part of my presentation is composite 3D printed grains. I will try to pass faster this section. This is devoted to our attempt to use 3D printing in improving of performance of engine in order to program its operation by using different materials along time of engine operation. Okay, the idea of this fuel grain was the following: that we have one surface exposed to hot flow, and the burning starts on this surface when other surfaces are protected, and they are burning with time, opening more and more space for fuel burning. So with this concept, we would like to have a constant income of fuel and a constant thrust of engine along its operation. This is quite a well-known problem, that when we are using solid fuel, especially simple geometry solid fuel like cylindrical fuel, we are changing constantly surface of burning, and we are changing the performance characteristic, for example, thrust and OF ratio. And with this project, we will try to keep constant this parameter using theory of hybrid propulsion, which is quite well developed nowadays. We try to design this fuel grain with the protection layer and to test. According to our calculation, these fuel grain is supposed to work around 10 seconds, burning step by step this grain. Here you can see time and the burn surface, programmed burn surface. So we did this also experimentally, and we proved the concept. This system works, but it's not that perfect as we planned. So I think we will need more further studies on this topic. But as initial stage, it showed quite interesting results. The results are these. We can see, especially on the right, that mass flow rate from the fuel grain total is constant. This upper curve here is the total mass flow rate of fuel when we are summing the mass flow rate of burning of paraffin and plastic. So when quantity of paraffin is increasing, the quantity of plastic is decreasing, and in total we have more or less constant value of mass flow rate. At the initial time moment, of course, is smaller, but then after we come to stationary regime, we have more or less constant mass flow rate. It means that amount of chemical energy provided inside combustion chamber will stay constant, and thrust of this engine flying at constant altitude also will remain same. Okay, we also calculated temperature inside combustion chamber. It was something around 1060, 1080 Kelvin. And chemical composition of combustion products a long time. It's just application of numerical method implemented in CA to estimate chemical composition. We did not measure this chemical composition since we have a quite reliable tool from NASA to estimate combustion. We can do it by this program. Okay, second part of my presentation is about liquid fuel ramjets. This is, I think, more important, more interesting because we have lots of results on this study. Okay, probably I will skip this motivation. The objective of liquid fuel ramjet was that we must have some engine which is working with liquid propellants. These propellants can be stored in separate tanks. So inside the engine, we will have just combustion chamber, and we will have some simple valves, maybe some pump to supply our engine. So we can make some kind of classical ramjet engine working on liquid propellants. Of course, it's a bit more complex than solid fuel ramjet because now it has some moving parts as pump, as valve, but is not that complex as other type of engines. So here we designed this engine to fly optimal conditions at 18 kilometers with Mach 3, but also since this kind of solution has to accelerate and change its altitude, we also calculated two other conditions, which are altitudes of 14 and 16 kilometers and Mach from 2.5 Mach to 75 as let's say acceleration regime, acceleration or deceleration regime. We calculated this off design conditions. The engine is this engine which I showed you on the previous one of the previous slides. The test bench is a bit more complex because now it requires much more components. We also have an air tank, and we have a valve. This is a big control valve, quite a huge size control valve. And it's slow because of this, because of inertia problem. It's slow control valve. We are measuring parameters before and after valve in order to provide an efficient control. We estimate temperature of inlet condition, and as in this previous motor, we have igniter to ignite the whole system, but we cannot use it as a gas vitiator anymore because the power is limited. It's like 80 kilowatt, and for this kind of solution, we need the power of few hundreds of kilowatts just for heat air. And because of this, we are using this external tank of propane, and we have a first stage combustion chamber, first stage, to heat the air. So at sensor 16 and 11, we have to reach conditions which typically can be found after the supersonic diffuser. Also, this engine can operate optimally for Mach 3 and also work in other regimes. Inside combustion chamber, we have also as a main fuel propane, liquid propane, and there is a flame holder, and injection system can be shown here. It's quite a long combustion chamber also for this kind of solution. At the end, we have a nozzle. We measure pressure inside combustion chamber. We measure temperature inside the material of the nozzle. We cannot, unfortunately, measure temperature inside combustion chamber because it's very hot, and the thermocouple will not resist such kind of temperature. Here on this schematic, you can see it's quite it's shrinked because I just needed some space, and the actual motor is 2 times longer, so it's just a half size. The complete size of the engine you can see on the top of this slide. We developed the diagram relation between temperature and pressure inside the heater with respect to desired Mach conditions and altitude. This is also published in IEC 2019, one of publications, and then we published it in other publications as well, especially I think last year we did something similar. Also, the combustion chamber of the heater is shown here. The idea is that our flow will reach temperatures required to and equivalent to a real diffuser, and at the same time it will not harm, will not burn the surface of the engine. So we have a flame holder inside which is preventing this harm of hot gas on the surface. So flow is separated into two regions. Internal region will maintain hot gas and flame. Flame holder will ensure that flame will not extinguish with the high velocity of flow. And this gap here, it prevents overheating of the wall. So cold flow, as you will see by our simulations, is passing on the surface of the wall, and this wall temperature is not exceeding the limit for material. The engine is made of stainless steel. The flame holder is made of high quality graphite. Okay, and the injectors are also, I think some heat resistant alloy of stainless steel. Talking about flame holding, it's extremely important. There are many patents that you can find on the internet. The idea is that you are creating recirculation zone inside flame holder. So after injection, or it can be combined with injection, you can organize this recirculation pattern inside combustion chamber, which will hold the vortex and the hot gas inside this vortex, keeping the flame on desired position inside combustion chamber. If you don't have this flame holder, for example, this flow will go out because of high velocity inside the engine, which is higher than combustion velocity, and this flame will be extinguished. So flame holder is a must-have inside the combustion chamber in order to hold the flame on required position. The nozzle of this engine is quite classical nozzle. Also, the nozzle insert is made of graphite, high-quality graphite, and this is quite good material for laboratory testing or laboratory application. Of course, for flight model is not that good because it's heavy and it's like a block of graphite. But as we know, in real application, you can use other materials for nozzle. CFD applied to this engine. I will just skip some parts. So to provide the CFD, we chose axisymmetric bidimensional simulation. And here our focus was on high quality meshing of this engine. As you may know, the quality of solution on computational fluid dynamics is strictly depending on the quality of the computational mesh. So we pay a lot of attention to make this mesh structured and well-organized near walls, so we can preserve the quality of turbulent flow and boundary layer on the wall. And also in the zones of flow recirculation and combustion, we have to have quite dense meshes. Okay, at that time when we made this simulation, I think it was maybe 4 or 5 years ago, we had limits of ANSYS. We did not have a full use of ANSYS license as we have now. And we had limit. ANSYS just gave us at most 512 elements for student license or academic license. And computers were not that powerful at that time. So it was quite important to choose number of elements and to make a mesh sensitivity analysis. And also another aspect which we have to consider, that motor is really long, and when you have a long computational domain, these reflections of waves inside combustion chamber and inside heater, they go in one direction, they return back to the heater and impact on boundary conditions. So the stabilization of computational process is also really long. We are talking about days. Even on this simple mesh of 512 elements, 512,000 elements, flow stabilization can take several days. These are examples of meshes, mesh 1, 2, 3, and 4. You can see structured mesh, which is following the idea which I explained to you before. And as the main criteria of choosing the mesh, we had analysis of heat flux on the wall, which was the most interesting parameter for us to answer the question if the engine will burn or it will survive. So we're testing with different meshes, looking, there is some difference. Okay, we choose, I think, mesh 2 or mesh 3. We didn't choose mesh 4 at that time because stabilization was really, really long and results are almost the same. So I think we chose mesh 3 for simulations. Okay, let me pass this mesh on the nozzle, mesh on the heater. Okay, and the mesh quality is okay. For this setup, for this simulation, we used predefined boundary conditions, fixed boundary conditions. We use K epsilon realizable model for turbulence. We used also radiation treatment for surface boundary conditions. Non-premixed combustion for chemical transformations. We used a specific model called GRIMAC3, which is quite well-developed, well-known model for hydrocarbon combustions, mostly for air propane, but also air methane also can work with propane and some light hydrocarbon, and it was completely suitable. We, unfortunately, at that time did not use any kind of two-phase model. The phase model, it's extremely complex. Even nowadays, it's really hard to couple this multi-phase model with combustion and compressible flow. So at that time, we used just gas as injection as fuel. Okay, some details on method of solution. It's mostly second order scheme, but in some parameters was first order scheme because it was not really stable. Results comparison between simulation and calculation, you can see really small difference. Deviation between temperature calculated and simulated was less than 5% at most in the heater, in the combustion chamber, and it's quite acceptable. So we can prove that our simulation was more or less good because it fits well with the NASA results. And these are the results of simulation, which show us distribution of temperature for different cases. These are 3 cases which I talked about. Case number 3 is design condition. Case number 1 and 2 is off design condition. We can see that temperature is concentrated on the center of combustion chamber. And on the surface, it's still lower than the critical temperature for the wall. And another work we have done with this was unfortunately I cannot show you today. Maybe next time I show you is a simulation of complete problem, combustion and heat transfer together. But then there we show that system has to survive the test. So this kind of experiment show us, numerical experiment show us a very important outcome is that our system will sustain the test. So we can go to practical implementation and practical testing of this engine. Some results on pressure, Mach number. As you know, Mach number will increase on the nozzle. Streamlines, showing also recirculation zones after flame holders. And also one thing which we did not expect, recirculation zone in the initial part of combustion chamber. This is typical for bidimensional simulation. After we provide a 3-dimensional simulation for this case, maybe one day I show you also this simulation, which is significantly more demanding on computational means. It also shows this, there is a recirculation zone in the center, in the beginning of combustion chamber, but it's not that bad as it looks on bidimensional simulation. Okay, mixture fraction showing the stoichiometric conditions of flame near the injector of combustion chamber, also injector on the heater. Okay. And as a conclusions, we see that deviation of results is less than 5% when compared to analytical results. Flow separation regions, they are keeping the flame, and combustion takes place in the central region of the engine, which we planned to have. The last part of this liquid fuel ramjet presentation is the test bench control. I think our time is quite limited, so I don't know if we continue with this presentation today, or we can pass it to the next time, because this part of presentation, I think it's extremely important. Just let me know if we have time, and we can continue.
Yeah. So, Alexey, thank you.
No, let me know if we can continue this presentation or we are out of time.
It's up to you, because I don't know what about your time.
Okay, so let's do the following. Since I already told you that we are simulated this engine, next time I will explain you how we plan experiment of this engine. So it will be, let's say teaser for the next part of my presentation. The problem was the following, that, okay, we simulated, we have this engine, but how in practice we can have a correspondence between test bench, which is on the ground, and with flight conditions, how we can show and prove that test which we are making on the test bench is corresponding to flight conditions. Okay, we can say, okay, we can satisfy it by measuring temperature and pressure inside the heater. So if we have conditions same to diffuser, supersonic diffuser, and flight regime in terms of pressure and temperature, we can say that we are flying at this and testing with the same conditions. But it's not that simple as it looks like, because this pressure and temperature on the heater, on the inlet of the engine, will depend on lots of parameters, mostly on conditions inside the air tank. It will depend a lot on control inside the valve. It will depend a lot on the ignition. It will depend a lot on how we control the heater by itself and combustion, this fourth stage zone. And also, we have to see that our engine is producing enough thrust for flight. So how we can get thrust without physically measuring thrust? This will be maybe another lecture or another seminar which we will have, I hope, soon. And these questions we can discuss further. And now I will be happy to answer your questions if you have some questions on this first part of my presentation. Thank you.
Many thanks, Alexey, for your interesting presentation. And I saw it was in chat some requests for questions. So you feel free, and you're welcome. Your questions, please. Maria.
Okay, hi. First of all, thank you for your presentation. That was really interesting. I'm sorry I missed the first, I suppose, 10 minutes, but still. So probably I missed this information, but can you tell us a little bit more about your testing environment? So was it in the university, at your university actually, or was it anywhere? So can you just describe a little bit more, tell us like a little bit more about it?
I think I have some problem to hear the question.
I also have, but as I understood, Maria interested within the facilities where it was performed in university or other.
Okay. Yes, everything we are talking about is made inside our chemical propulsion laboratory, everything inside university. And your question is really good. You're really interested because it doesn't look like made inside university, because we have to have a lot of infrastructure to provide such kind of design. And of course, for theoretical calculation, there is no big problem, because we have literature from the past. Everything is published about ramjet. It's quite well-known engine, so we could make a preliminary design. The problem was when we tried to simulate. There are not so many scientific works on simulation of such kind of device. And then when we try to build, there is absolutely zero amount of works about testing. There is a quite well famous school of Alongani from Israel, who was working, I think, all his career in the area of rockets and ramjet and the military application of these devices. And Technion University, and very famous. We met personally one day, and it was a wonderful meeting. So School of Alongani published lots of very useful information about how to make things work, and we try to build it with the help of our research foundation, different research foundations. I think the first project we got was from Federal District, from our local research foundation. And it was quite a risky project because we were quite ambitious putting these subjects, which nobody studied before. So it was very difficult. And the development of this project took from 2013 to 2019, maybe 6 years, more or less, to build all the infrastructure. And then it was easier because we proved the concept and we got more funds for this research. Nowadays, I know that there are many interested parties to finance such kind of activities inside Brazil. And we are working to continue this research on a higher level. But all infrastructure we made, it was inside university. And quite interesting to note that you cannot buy equipment, lots of equipment for some dedicated activities from the market because of several reasons. One, market does not exist for such specific application. And second, there are restrictions on some importation or some specific technologies that we have to overcome. So we developed by ourselves many subsystems. As I already explained you before, for example, flow control valve, ignition system, control system as a whole, we developed by ourselves. We could not buy it. So this is why it took so many years to develop this project. And until now, we are still continuing with this project. I think it's very important for many, for some government institutions interested in such applications. So I hope soon we will have more projects on this area.
Okay, thank you. It's very impressive when something is performed from the idea to the real life. It is a question about the possibility to download the presentation. I guess we'll share the record of this presentation, if you don't mind, Alexey.
Yes, of course. We will share this video. All materials are published in the literature from our authors and co-authors, so there will be absolutely no problem to share this video as well.
Yeah, that's great. And you may find it in Facebook, in аерокосмічний факультет. So if you'll please subscribe here, and you'll find all these materials on that.
Yeah,
Okay,
thank you. Thank you very much. Unfortunately, I don't have Facebook account. I'm like old school guy. I don't have Facebook account. I don't have Instagram account. Sorry for that.
But I also, but it was a necessary instrument for the communication.
Yeah, I see.
I not prefer it. Okay, other questions? Because I have a question about that phenomena in the chamber that perform a circulation in the inner chamber. What was the reason of that? Because I'm really surprised to find it.
This one?
Yeah. What was the reason? Because I know that sometimes we try to find some circulation to perform for cooling process, such packs, let's say air packs, but how, maybe you have some explanation of reason.
Yeah, first of all, we must have circulation on flame holder. So when we have flame holder, the main goal is to have circulation. So these recirculation are quite welcome because they help us to keep the flame. When we are talking about the central bubble, this was also a surprise. I think it happens because of high velocity flow is passing here through expansion of area, and this because of flow deviation, velocity deviation, happens this process of circulation. And I will tell you that this is maybe also a numerical result, because on three-dimensional simulation, this recirculation has different shape. So I would like to test, and maybe you understand that to test this bubble in real ramjet is not that easy. You cannot just open and see, there is a circulation or not. But I think we can find some kind of indicator and to test this. I think this bubble is just because our structure is not perfect. The structure is not perfect. So the section of flow expansion, as you can find, where is I think this picture is better. It's still shrinked, but I hope you understand that this motor is 2 times longer. It's not that short as it's shown here. And is not perfect. The shape is not perfect. What is this shape? This shape is a transition between, I think, 3-inch pipe or 3-inch pipe to 5-inch pipe, and standard transition you can buy on the market. And since this shape is not perfect, this circulation is happening. But I'm not worrying so much about that because it happens way earlier before fuel injection. So when we will inject fuel, I hope at that time flow will normalize and stabilize at that section. What can be done to prevent this kind of recirculation is a flow straightener. So on this junction here between heater and combustion chamber, we can put flow straightener, which are pipes or meshes, which will mitigate such kind of recirculation. So I think this is a viable solution to solve the problem if this problem will affect on performance of the engine. Until now, I did not see any kind of problem, but let's see. Let's see in the future if we must prevent this. I think flow straightener is a good option to prevent such problem.
Okay, thank you. So, other questions? Maria, you're welcome.
Yeah, thanks. So, Alexey, sorry, it's a little bit loud here. So, Alexey, can you tell us maybe some tips and tricks, or what was the hardest part for you during this experiment, during this project? I mean, we have some, let's say, engineers who want to develop rockets or, I don't know, missiles. So what should they expect? Yeah, some difficulties, which was the most challenging, I mean, on top of getting money from the government or something like that. So any, I don't know, top 3 of your most difficult things you faced?
Thank you for your question, Maria. I think, yes, we have several difficulties in this project. Maybe I will tell you the simple things and then more difficult things. Simple thing is to build a cycle of engine by itself, because it's quite well described. You can maybe make a design of this engine is not that difficult as a tube, as a pipe, because you can find many solutions already published. The problem, for my opinion, of this particular engine is flame stabilization and injection and flame stabilization. So it must be efficient to keep flame on the flame holder, and it should not burn the wall of combustion chamber. So you have to prevent in some way the problem of overheating of the wall, and stabilize flame, keep flame on its position. Also, since if you can have some kind of problem with this, it can damage also other parts of engine. For example, injection, flow recirculation. If you make some kind of wrong design, flow can return even to injector, and flame can return to injector. And we can find the burning of injector because of flow recirculation. These problems typically they are solved quite well. Let me show you the first slides of my presentation. If we are okay, it was a long presentation. Okay, this, for example, the Taurus missile. I think it's one of the most perfect engines for me. I think it's one of the best. It uses flame holder of like mesh flame holder, and also it uses bypass of cold air to cool down the structure. But one disadvantage of this solution also exists always. I think two disadvantages. Disadvantage number one is you have to have access to special materials, which in Brazil is very difficult. So we could not make such kind of design, which I was thinking first, that just because of restriction in use of advanced materials, we could not make this flame holder, this design of flame holder. And the second, the question of technology. Yeah, access to materials and technology. We don't have also. So we cannot have this access. So in our application, in our engine, this flame holder made of graphite was a compromise. What we have and what we can realize from technological point of view. So I think this is the most challenging problem of this project. We have to keep the flame on the place where it has to be, and it should not damage the engine. So I hope I answer your question.
Okay, thank you. Please ask the questions, because as I know, Alexei, are very restricted in the time today. So hurry up. Maybe my small question about the technology. The technology of production, you mean, or it's a problem of production of this flame holder, or all these parts of the aft section of the rocket? Could you clarify, Alexei?
I don't know the problem of production, because since we are working in the laboratory, we just make a few pieces. Very few pieces. But the problem of this specific flame holder, it's made of thermally resistant alloys, and we don't have this in Brazil. You know, it's from United States, so it's totally different technology.
I understood.
We work with what we have. And we are inside university still, we are not industry. So we were a bit limited on budget and access to technologies. I think this we will overcome in very, very near future, since we have interested parties on this continuation. Maybe we can use resistant alloys and additive manufacturing to solve the problem. So this is another solution.
Yeah, it was the next my question about the additive technologies.
Yeah, okay. And I hope this will be our next project.
Okay, thank you.
Maybe the last comment I would like to make for you today, this development I show you, they are university development, so they are low TRL development we are talking about, from 1 to 4, not higher than TRL 4. So also limited on budgets, on access of technologies. And we are justifying our work by doing scientific studies, scientific research. So this is what is driving this research. I know it's not 100% scientific because we are trying to push the limits, push the boundaries, and make some applications. And this is what is attracting other companies to work with us. That we are working in a bit different way that the classical university is working. We are not just teaching classes. We are trying to build some real structure, maybe on low tier level, but which can be then advanced to higher levels.
I see. So Anna says that she is impressed from your presentation, and I guess it's a good ability to say that it's and a part of our lessons. And in near future, I hope you'll see the next presentation of Professor Олексій Шинкаренко that familiarizes you with problems, not problems, challenges in the rocket industry.
Yeah. I think we can keep these seminars for future. So I am quite feeling quite comfortable here with you. So I think we can continue with this collaboration. And I hope some of my students will participate next time. I don't see if someone from UNB joined us. I think no. Even though when I share the link, okay, people are actually motivated, but now, as I told you, we are very close to Christmas, so they are occupied with the family and not with the study. Yeah, but I will also make available this presentation for my colleagues and my students, and they will assist for sure.
It will be good because I have some messages that some participants could not connect due to the problem with the internet and blackouts in the different regions of city. So it will be good to share this presentation with them.
Great, let's do that. Okay, I think I can stop my recording at this point. We can continue next time from a point I stopped about practical construction and calculation of this device. If you will be interested, or we can go to other topic as we decide. Let's see. I think our next meeting can be in January if you work in January, or if you have vacation time, we can work on further.
No, I guess it will be suitable in January.
Okay, great.
Okay.
So let's think about the next meeting in January.
Yeah, for sure. Many thanks, dear Alexei, for your presentation. And I wish a good evening for everybody, quiet night, and see you on next our meetings in the rocket sites.
Thank you very much. See you next time.